So we're imagining a length of copper wire. We want to know what is the actual drift speed of the electrons in that wire. We've got a radius of it of 900 microns. In other words, it's 1.8 millimeters in diameter. And we're going to assume that there's 1 electron per copper atom. Now, let's say that there's a current going through it of 17 milliamps. Now, what we know is that current density, which is current per unit area, is NE times the drift velocity. So current we know, area we can easily work out. We know the charge on an electron, and drift velocity is what we need. So really the thing we're going to start by finding is N, which is the number of electrons per unit of volume. And we're assuming 1 electron per atom, so we're also saying that that is the number of atoms per unit of volume. Now, just a bit of chemistry here. It is in fact the number of atoms per unit of volume will be Avogadro's number times 1 over the molar mass times the density. And the reason is that atoms per unit of volume will be atoms per mole times moles per unit of mass, which is 1 over mass per mole, times mass per unit of volume, which is density. So that gives us Avogadro's number times 1 over capital M, the molar mass, times rho. Now, I'll put it at the side here, but rho for copper is 8.96 by 10 cubed kilograms per metre cubed. And the molar mass of copper is 63.54 by 10 to the minus 3 kilograms per mole. So that gives us N is Avogadro's number times the density over the molar mass and that gives us the large number of 8.49 by 10 to the 28 copper atoms, or really we want to know electrons per metre cubed. So I'll continue with this on the next page. So we're nearly there. We have current density being current over area equals N, which we now know, times E, times the drift velocity. So that means the drift velocity is current over N times E times the cross-sectional area. Now, the area of that wire, pi r squared, which will be pi times 0.9 by 10 to the minus 3 squared, will be 2.54 by 10 to the minus 6 square metres. So our drift velocity, 17 milliamps, over N that we worked out being 8.49 by 10 to the 28 electrons per cubic metre. The charge on each of those, 1.6 by 10 to the minus 19 coulombs, and the area there being 2.54 by 10 to the minus 6. And that gives us a drift speed, which may or may not surprise you, of 4.9 by 10 to the minus 7 meters per second, or if you work that out, it turns out to be about 1.8 millimeters per hour, which is surprisingly slow. However, since changes in an electric field travel at nearly the speed of light, that means in any given wire, as soon as the voltage is turned on and there's an electric field, all of those electrons will start moving at practically the same moment. So even in a long wire, it isn't going to be a long time for the electrons to travel from one end to the other, because the wire's full of electrons and they all start to move at the same instant. And really, of course, current, we remember, is just how many are passing per instant and not how fast they're going.